I've been a TA for algorithm courses for a couple of terms. One important topic that both the professors and I find it very hard to teach effectively is the reduction between NP problems. And we believe this is because how we teach this topic currently. So currently, the instructors and the students working on reduction exercises with pen and paper. So they first came up with an idea and then try out on this idea with a couple of simple examples. If the reductions looks okay, looks nice on this set of simple examples, and then it's considered done. And it gets written on a piece of paper or it gets typeset in LaTeX, say in pseudocode. However, the big issue with this approach is that this really not much confidence for the student that whether the reduction they come up with really works on all examples because they have only tested the reduction on these simple, not rich enough set of examples. And for the instructors, they also have a very hard time of figuring out whether a claimed solution to a reduction is indeed correct. So I'm not exaggerating. This is actually a screenshot taken from an online algorithm textbook that's trying to visualize the reduction from 3-set to Hamiltonian cycle. It's 100% okay if you forget what exactly the Hamiltonian cycle is. But probably you can see from the picture, the structure is really involved and perplicated. You're not alone. Unfortunately, it turns out the instructor creating this visualization also is confused by the perplex structure of this reduction. And there is actually a counterexample for this reduction. Probably I'll get impressed if someone you would like to construct handcraft such a counterexample for each student in your class. Maybe some PL people have the data patience. So our life will be a lot easier if NP reductions were actually programs that we can run and random test. So we introduced Karp, which is a domain-specific language, which is pedagogically motivated that help people to formulate reductions precisely and formally as programs that can be run, random test, and debug. With Karp in hand, a user now precisely and formally formulate their reduction ideas as a Karp program, and the Karp randomly generated the instance to test this reduction. So this changed the pedagogy completely. Now the student enjoys the full benefit of a programming language such that they can run, test, and debug their reductions. And the instructors are relieved from the burden of manually construct counterexamples in order to falsify a reduction, the correctness of which they are unsure of. So in order to accomplish this acclaimed goal, Karp combines a series of interesting research ideas in programming language. But unfortunately, for the sake of time, I cannot talk about all of them. If you're interested to look at more details in the paper. As for today, I'm going to briefly tell you how it looks like to do a reduction exercise in Karp, as well as introducing you to the property-based testing in Karp. So before that, I'm going to take a detour and do a recap of NP problems and reductions. So formally, when we talk about NP problems, we are actually referring to decision problems, which problems with yes/no answers. So NP problem can be defined by its verifier. Basically, the verifier takes an instance and the candidate proof of this instance being yes, and either accept or reject in polynomial time. So if the certificate is indeed a certificate of this instance being yes, then it will get accepted by the verifier. In this case, we call this proof object a certificate of this instance. And for any yes instance, there always exists such a certificate. On the other hand, for no instances, there does not exist such a certificate. And no matter you trying to pair some input with the instance as input to the verifier will reject in polynomial time. So a reduction basically is a function that maps the instance of one problem to that of the other. However, not all functions that map instance to instance are correct reductions. A correct reduction is expected to map yes instance to yes and no instance to no. So now we're on the same page about NP problems and the reductions. Let me tell you how it look like for students. Usually, they write the reduction exercises on paper. So before defining the reductions, there will be some formal definitions for the problems that reduce from and reduce to. The problem definition will consist of two parts, which is the problem structure, basically specify the data structure of the instance and certificate, and the domain of the verifier. And of course, there will be the verifier. After we have the problem definitions, then the students start to define the actual reduction, which is the instance transformation function that maps the instance from one end to the other. As we have seen that not all instance transformations are correct. So besides that, we usually ask students to provide some sort of evidence or proof of correctness for the instance transformation, which usually this is done in forms of some certificate mappings that maps the certificate back and forth. So actually, this is exactly the thesis of a reduction exercises as a Karp program. So in the next 5 minutes, I'm going to show you, walk you through the code of a reduction in Karp using a specific example. I'm going to mostly focus on the instance transformation as the certificate transformations in a similar manner. If you're interested, you can find the complete code in our paper. So the example that we use will be the classical example from the reduction from 3 set to independent set. And here I have a minimap that's showing where we are, exactly where we are in the description of the structure of the reduction exercise that we have just seen. So we first start by defining the 3 set problem in the sublanguage Karp problem definition. So here we need first to define the problem structure. So for 3 set, basically it has the instance of CNF, which has array T3, and the certificate of the 3 set instance basically is a mapping from the set of variables of that CNF to the medium of Boolean. After defining the problem structure, we get another definition form which we can use to define the verifier. So the verifier basically is a predicate that takes 2 inputs, the instance and the client certificate for that instance. And the body of this reset verifier basically checks if for every clause there exists some literal in that clause that is satisfied under this incoming certificate. Okay, we will do the similar thing for independent set, but just as a recap for people who forget about what independent set is. So an independent set instance basically consists of a graph and a number, and the valid certificate for the yes instance is basically is a subset of the vertices that is at least the size of the given number, and no 2 vertices in the subset are neighbors of each other. For example, here 1, 3 is the independent set of side 2, but if you pick 1, 4, it will not be independent set because they share an edge. Okay, so this is exactly what we usually write in code. So they will say, hey, I have a problem called independent set, and the structures I have a graph which is undirected, and I have a k which is a natural number, and the certificate is basically the subset of vertices of that graph. And similarly, the verifier basically does the checking that I just said. It checks if the incoming certificate has at least a size of k, and the no 2 vertices neighbors to each other. And this is actually exactly also matches how we write in paper the verifier would be. So now we have the problem definitions. Let's move on to define the actual reduction from 3 set to independent set using the sublanguage Karp reduction. So the instance transformation, which is the actual reduction, is defined in Karp using the defined forward instance construction definition form. And in the body of this function is basically inspect the given instance or the 3 set instance, take it apart, and create the vertices and the edges of the graph, which eventually becomes the resulting independent set instance. Okay, so let's look closer how this kind of construction will look like. So actually, almost all structures in the reduction language are created using comprehensions or finite objects, such as this one, when we create when we want to create these vertices from the literals. So basically, you write a comprehension, let's go over all literals from all clauses and create an element for each of these literals. In the same way, we will also create the triangle edges that will connect the vertices that correspond to literals from the same clause. And we also have the edges shown in blue that's connecting the triangles together. Finally, we put everything together to form the graph, as well as concatenate it with another field, which is the corresponding to the number of clauses in the given CM. So just to remind you that a correct reduction is back to map a yes instance to a yes and no instance to a no. However, sometimes people write buggy reductions, which does not satisfy the aforementioned property. One example of this is a common mistake that people make. You might forget the edges that form the triangles. So, which will lead to a graph which does not have these edges in red. Now we know that reduction is a program, and we want to run it and we want to test it, and hopefully we want the test to be able to figure out this bug. So the most straightforward way to do this is to handcraft some examples and apply this transformation on these handcraft examples. But unfortunately, as we can see here, if we simply test some handcraft examples like this, it's actually often unable to uncover the mistakes of this underlying reduction. And because of these handcraft examples often very simple and it's biased, and it will give you complacent and false confidence that discourage you from testing more. So in order to counter this, Karp is equipped with some facilities for you to automatically to generate instance, so the user can automatically get instance to test their reduction. So this is the result that I showing when I just run the random testing on this buggy reduction, and it actually shows a counter example which this reduction maps a no instance to a yes instance. So let me now tell you how this random testing works. So in order to random test the instance transformation, of course, we need instances. So Karp derives instance generator from the structure evolution that we have just seen before. However, just have instances is not sufficient to describe the correctness of instance construction. We also need to test whether a yes instance is mapped to yes and no instance is mapped to no. So the way to do this is we need problem-specific solvers. However, if we ask our students to write a solver for every reduction that they're working on, they probably will spend all their time figuring out these solvers instead of working on reductions. So Karp automatically derives the problem-specific solvers from the verifier. In order to accomplish this, Karp utilizes the solver-aided technologies. So the verifier code in Karp is translated into the solver-aided programming language Rosetta code. And given a concrete instance that we want to solve, a symbolic certificate is paired with a concrete instance as input to this translated verified code. And then Rosetta symbolically execute the pair, and if it successfully solved and produce a concrete certificate, then we know that this instance is yes instance. Otherwise, if it's set, then we know this is a no instance. So we will be able to check the correctness property. Now let me switch gears and tell you more about the Karp in practice. So we asked two research questions to evaluate the expressiveness and the efficiency of Karp. So the first question basically asks, is Karp sufficient expressive enough to capture a wide range of reduction exercises? And the second question asks, is Karp's probability-based testing sufficiently efficient to properly test a wide range of reduction exercises and detect mistakes? So for the expressiveness evaluation, we took examples from this widely used classical textbook by Climber and Turtle in Cornell. And so we successfully formulate 26 reductions from this book. So 5 of them are from the text, which are solved with examples, and 21 of them are from the 42 after chapter exercises. So for the remaining 21 that we did not completely formulate, we conjecture that 14 of them will be rich because they share the similar structures as one that we successfully formulated. And there's no limitation that 7 of the remaining problems that is currently inexpressible in Karp. For example, there are problems involving strings. But at this point, we do not have string library support in Karp. So for the efficiency evaluation, we conduct some experiment on a typical student laptop with the configuration still there. It's actually this laptop I'm actually using. So for the aforementioned 26 correct reductions, actually the average time for each of them running 10 random instances, conduct 10 random testing is no more than 2 minutes. Okay, some random test people might say, hey, this number 10 is so small comparing to what they're used to, like millions of tests, automatic testing. However, remember here, in order to conduct each test, we need to have called the solver twice, and these are usually hard problems, these NP hard problems. We will call the solver twice, and in fact, we'll see in shortly that despite the small number, the random test is actually effective and detects bugs. So in order to test the effectiveness, we also implement the one buggy version for the 10 of the both reductions. And each bug is not just random mutations. We sort these bugs from these factors from their previous teaching experience, and also including other bugs that we found during our expressiveness evaluation. For example, just examples of these bugs are the 3 set to independent set mistake that you have seen, and also the Hamiltonian cycle reduction in the beginning of the slot. So all these buggy reductions are caught by testing no more than 20 random instances. So the random testing is actually pretty effective despite the number is small. And since this 20 instances is just no more than 5 minutes. Lastly, since we are talking about adoption the day before yesterday, let me tell you something that is not in the paper about adoption of Karp. So we have tried Karp in 2 terms of algorithm classes at Northwestern, and we received positive feedback both from instructors and the students. Since this is not formal enough, I might not say anything more about it, but there is an ongoing development to turn Karp into a web service, and there are some formal user study which is ongoing. Lastly, as a final note, soon Karp will be at an algorithm course near you.
Most NP reductions introduce a lot of symmetry in the thing that they produce because they reuse a gadget over and over. Does that cause any problems for Rosette or the solver underlying it?
Currently, because we are not solving very large-scale problems, right? Because we want to find conic examples that are interpretable. So we have not experienced serious performance issues. So also because we have some careful encoding for these problems. Okay, if you're interested, we can talk about that more. So I think we have not experienced any performance issue with that.
Hi, thanks for the great talk. That was really interesting. I was wondering if you could speak to the way that you generate the instances of the problems, right? You sort of generate them at random and then feed them to the solver to decide whether or not they're yes answers or no answers. I'm curious about sort of when you randomly generate instances, how often do you get yes answers and how often do you get no answers? Because one could imagine that you could sort of generate random instances and the satisfiable solutions are very sparse in the total space and you always get no answers, and then it's not sort of an interesting testing of the problem.
This is a really interesting point. So because actually we spent some effort in order to alleviate this problem. So basically, yeah, we are mostly using random generation for the instance. However, there is some prior work on the phase shifting behavior for these hard problems. So for example, 3 set. For 3 set problem, there's some phase shifting behavior which basically saying for certain parameter combinations, for example, the ratio between if you consider instances that have the number of variables and number of class ratio around a certain points, then it will there will be, if you generate instances with these kind of parameter combinations, it will be likely you will get both yes instances, no instance. So basically, we take advantage of this kind of phenomenon and generate it. So our generator building from the bottom top fashion, and basically we have these phase shifting generators for each of these small blocks, and after for particular instances, then we just build in the generator for this instance from these small blocks.
Oh, thanks for the talk. A quick question. So one thing you didn't talk about that a reduction needs to satisfy is this polynomial time guarantee. Have you thought about how to ensure that the user writes a program that's actually running in polynomial time?
Yeah, this is actually also very important, insightful comment and questions, because actually we get the same questions from the reviewers during the rebuttal. So actually, so you notice here, I said most constructions, almost all the constructions in the reduction language are these comprehensions or finite objects. So basically, we actually have a theorem which based on big step semantics, which is a loose bound, proving this. You cannot write the expressiveness of the language restricts the language restricts your expressiveness, so you will not be able to express constructions that will take super polynomial time proportional to your input.
All right, let's thank the speaker one more time.